Hi, I am Donalek, and this is the third and last module of the Introduction to Machine Learning as part of the JPL Caltech Virtual Summer School on Big Data Analytics. In this lecture, I'll focus on unsupervised learning. Last time, we have talked in more details about supervised methods. Today, I'll define unsupervised learning and its most common uses, introduce the basic concepts for clustering, and briefly introduce another type of very interesting learning approach, reinforcement learning. Now, the problem in unsupervised learning is trying to find hidden structures in unlabeled data. The model is not provided with the correct results during the training, unlike the supervised training. And so the goal may be cluster the input data in classes on the basis of their statistical properties only. For example, suppose our data points spread like the ones in the picture, we can immediately tell that they tend to form a tree cluster. The most used models are listed on the slide, and the next lectures we'll see some of them in more details, especially k-means and self-organizing maps. Now, clustering, modeling, data density, and dimensionality reduction are among the most common problems addressed with unsupervised techniques. Clustering can be defined as the task of assigning a set of objects into groups, called clusters, so that objects in the same cluster are more similar to each other than to objects in other clusters. Related to the clustering is also the search for outliers, where we try to find objects that are distant from all the clusters. These may turn out to be errors, artifacts, or very interesting objects. And also, unsupervised learning is used in many algorithms for dimensionality reduction, both for feature extraction and feature selection. And this will be covered in another series. Now, let's see some applications. Unsupervised models are commonly used in genomics to reduce the dimensionality of high-dimensional data sets that may contain hundreds of thousands of variables. Market research or market segmentation is another area when they are commonly used. The goal there is to discover distinct groups in the customer bases and then use this knowledge to develop targeted marketing campaigns. Clustering and other unsupervised approaches are also used in astronomical data analysis, data compression, outlier detection, social network analysis, image segmentation, basically in almost every field. Now, clustering models can be divided in three major groups: hierarchical, partitional, and density-based approach. In partitional clustering, all the instances are placed in exactly one of k non-overlapping clusters, as shown in the figure where we have three clusters. Now, during this process, many partitions are built and then evaluated based on some criterion. In this approach, the number of clusters k is given in input and may come from external or expert knowledge or from an optimization algorithm that aim to find the best k. And k-means is a typical partitioning method. While in a hierarchical clustering, we try to find subsequent clusters using previously established ones. Hierarchical methods can be further divided in agglomerative or bottom-up and divisive or bottom-down. In the bottom-up approach, we start with each element in a separate cluster and merge them accordingly to a given property. On the contrary, with a divisive approach, we start with all the points in the same cluster and then start dividing them. The third approach is the so-called density-based approach, and it's based on connectivity and density functions. Here, clusters are defined as areas of higher density, and higher density than the remainder of the dataset. Objects in the sparse areas are usually considered to be noise or border points. Now, one of the key concepts in unsupervised learning is labeling. We have said that labels are not used during the training process, but if we have them, we can still use them to analyze the results. Even if we have labels for just a small number of objects, we can project them into the clusters and have a better idea of the objects that are in each cluster. For example, we can see if objects of the same classes are actually clustered together. Now, since in supervised learning we don't have targets, we cannot compute errors or use other accuracy measures as in supervised learning. So how we can define what's a good clustering? And we can do that using internal and external measures. External measures are related to how representative are the current clusters to the true classes. And we can do that using labeling or actually having experts looking at the clusters. Internal measures look at intracluster and intercluster distances. Basically, we can say that our clustering is good when the intracluster distance is minimized and the intercluster distance is maximized, as shown in the figure. In the figure, you can see that points belonging to the same clusters are very close to each other, and they are far from the points of the other cluster. Of course, the one pictured is an ideal situation, because real-life problems are usually much more complicated than that. Now, if we want to give some more formal definition, we can say that the intracluster distance can be defined as the sum of the distances between objects in the same clusters, while the intercluster distance can be defined as the distances between different clusters. So one is related to the points, and one is related to the cluster. In these slides, there are some alternatives to calculate the distance between clusters. And they give also a measure of the quality of the clustering and can also be used as a linkage criteria in hierarchical clustering. For example, single link is defined as the smallest distance between an element in one cluster and an element in the other. On the other hand, complete links is defined as the largest distance between an element in one cluster and an element in the other. And it's easy to notice that distances have a fundamental role in unsupervised clustering, because they define the similarity between clusters and also define the shape of the clusters. So in the slides, there are some of the most common used distances. For example, the Euclidean distance is probably the most used, but be careful because it is extremely sensitive to the scales of the variables, so it may be a good idea to apply some sort of regularization before applying it. And while in the taxicab or Manhattan distance, the distance between 2 points is defined as the sum of the absolute differences of their coordinates. For example, in the figure, to go from point A to point B, there are different paths, and the red, blue, and yellow lines have the same taxicab length, while the green line is the only shortest path using Euclidean distances, a Euclidean geometry. Now, what about if we have to deal with strings? Also, in the case of strings, we can apply ad hoc distances. For example, the Hamming distance or the edit distance. The Hamming distance can be defined The Hamming distance between two strings of equal length can be defined as the number of positions in which the correspondent symbols are different, and this is most used for binary strings. And in this example, the two binary strings have an Hamming distance of 3 because they differ just in 3 positions. So basically, the Hamming distance measures the minimum number of substitutions required to change one string into the other, while the edit distance is defined as the minimum number of edits needed to transform one string into the other. For example, let's consider 2 words, biology and its translation in Italian, biologia. And we can see that the edit distance is equal to. That's because we can transform biology in biologia using just 2 operations. First, we need a substitution. We need to substitute y with I, and then we need to add a at the end. So we can basically tell that the edit distance measures the amount of differences between 2 sequences. Now, there are many variations to the edit distance, and one of the most used is the Levenshtein distance, that is named after a Russian computer scientist and allows insertion, deletion, and substitutions. Other variants allow only insert and deletion. Now, when dealing with distances, normalizing data is often crucial, because with normalization, we can adjust values measured on different scale to a common scale. There are many different types of normalization, like zero mean variance 1, normalizing all the values in the 0-1 range, logarithmic and softmax normalization, and so on. Actually, the choice depends on the data and purpose. For example, with the min-max or range normalization, we have the advantage of preserving all relationship in the data without adding any bias, while the soft-max normalization is a way of reducing the influence of extreme values or outliers in the data without removing them from the dataset, and that's very important. Now, before wrapping up, let's introduce briefly another interesting learning model, reinforcement learning. In supervised learning, you are given input and corresponding outputs. In unsupervised learning, you are given just the inputs. In reinforcement learning, you are given input, some outputs, and a grade. The grade defines how well you are doing if you choose this output. Basically, each output in reinforcement learning has a positive or negative reward. This is most used in gaming, where the computer can play billions of games against an imaginary opponent, learn from that, and the moves get a positive or negative reward depending if they lead to a win or a defeat. One of the most notable examples was, or is, Chinook, that became the first program in any game to win a human world championship. By 1996, it became clear that the program was unbeatable and was forced to retire. Now, as a summary, in this module, we have defined unsupervised learning, its goals and application, and we have also introduced the clustering that we'll see in much more detail in one of the next lectures. I have also briefly introduced another very interesting learning, the reinforcement learning. And that's the end of this series of 3 lectures on the introduction to machine learning.